So now I am furthering our endeavors in thermodynamics, and I am going to just talk about the specific heat capacity, which we have already done in another lecture beforehand. And there I am just defining the heat capacity, which was defined as delta Q upon delta T. And then we define the specific heat capacity per gram, okay, per unit mass. So I divide S by M, I get 1 upon M delta Q upon delta T. And finally we say that the specific heat capacity per mole, where N is the number of moles, so I just divide the S by N and I get 1 upon N delta Q upon delta T and joules per mole per Kelvin. Okay. Then for the gases in particular, we define the specific heat capacity per mole as Cp and Cv. So here I am writing 1 upon N delta Q upon delta T P. This means, this subscript over here means that the pressure is constant. And similarly for the Cv, which is the specific heat capacity at constant volume, I write 1 upon N is equal to delta Q upon delta T at when V is constant. I could write here P and V, or I could write that delta P is equal to 0, delta V is equal to 0. So it doesn't matter. Now what we find in the case of gases, and in particular for the ideal gas, which is a rarefied gas, okay, rarefied means its density is small, okay. At ordinary room temperature and of course atmospheric pressure, these things are defined. So we will find that Cp minus Cv is equal to R, where R is the universal gas constant. How come? We'll look at it a bit later. Now let us see as to consider a solid single mole where N is the number of molecules, but N is a specific number which we call the Avogadro's number. The Avogadro's number N is equal to 6.02 into 10 to the power of 23 per mole. Okay. Now it is found that which we will work out in later on in the oscillations of delting, okay, for a single molecule, the average kinetic energy of an oscillator in one dimensions. If it is vibrating in, it is oscillating in one dimensions. So this is equal to 2 times half kBt, okay, where kB is the Boltzmann constant. So this 2 and 2 cancel and becomes equal to kBt. Now in 3 dimensions, because there are 3 independent directions, as I told you, because the angle between all these directions is 90 degrees, so cos of 90 degrees is equal to 0, so there is no resolved part in that direction. So in 3D, we just multiply it by 3 and find that the value is 3 into kBt, okay, from here to here. Now therefore the internal energy of the solid for a single mole, this will become equal to 3 kBt into N, but kB into N is equal to R, capital R, the universal gas constant, like this, and therefore I can define the specific heat capacity is delta U upon delta T, delta Q upon delta T, and because the two are equal, so I can say that delta U upon delta T. Why? Because there is no work done. So delta Q is equal to delta U in the case of solids, because there is hardly any disturbance regarding the volume of the solid. So this turns out to be equal to 3R for solids. Here I am just telling you about R, 8.31 joules per mole per Kelvin, Boltzmann constant, Kb 1.38 into 10 to the power minus 23 meter square kilogram per second square per Kelvin, and Avogadro's number, of course, 6.02 into 10 to the power of 23 per mole. And it is emphasized that every mole of any substance, the number of molecules whether in the solid state or liquid state or gaseous state is of course equal to the Avogadro's number. So Avogadro's number is also a kind of a universal constant as studied in physics and chemistry. So we will derive now this formula, Cp minus Cv is equal to R in the case of an ideal gas, for which the mother equation is, the zeroth equation is Pv is equal to N or T. So we are to prove Cp minus Cv is equal to R, I told you. And for that the starting equation that we are taking is delta Q, change in the internal energy of the system, the heat given to the system, which is absorbed by the system, is equal to the change in the internal energy plus P delta V, okay, for system of the gas that we are going to deal in. Now we can say that if delta Q is the heat absorbed or the energy absorbed at constant volume, that is when delta V is equal to 0, there is no change in the value of the volume, then Cv we have defined and is delta Q upon delta T at constant volume, which we can write as delta U upon delta T at constant volume, and we are going to drop the subscript V and write it as simply as delta U upon delta T, and the subscript has been dropped as the internal energy of an ideal gas is a function of temperature only. Temperature only. And similarly, if delta Q is heat absorbed constant pressure, that is delta P is equal to 0, then by definition Cp is equal to delta Q upon delta Tp, which when we differentiate we get delta U upon delta T over here, and plus because P is constant, so I take it as a constant, delta V upon delta T at constant pressure. And again this I write as delta U upon delta T plus P delta V upon delta T P. Again for the same reason, the subscript that it was there, we drop it here and write it as delta U upon delta T, like that. This subscript of course we retain for the reason that the internal energy of an ideal gas which is rarefied has less density is equal to, is a function of temperature only. Now let us write this equation. I said zeroth equation, Pv is equal to nRT, where n is the number of moles. So if we take a single mole of an ideal gas, then we have Pv is equal to RT. And if we differentiate with respect to temperature, then we write P delta V upon delta T is equal to R, is equal to R, because delta T upon delta T will become equal to 1. So this relation goes equal to R, and I can substitute it here and get the value of Cp minus Cv is equal to R. Cp minus Cv. So look here friends, this is a very simple thing, and once you do it 2 or 3 times, you can always scribble it, I believe, with the fast energy of your hands in a matter of about 80 to 90 seconds. and you can write everything over here and derive it and be happy about it. We'll talk about the thermodynamic state variables and the equation of state. Equilibrium state of a thermodynamic system. It is defined in terms of specific values of some macroscopic variables, also known as aka, also known as state variables. In fact, there used to be a film by the name of aka gaseous plane. Okay. So, for example, in the gas system, we specify these variables in terms of the measurables: pressure, volume, temperature, mass, and in case of mixtures, we also have to define the composition of the mixture of gases. We find that a thermodynamic system is not always in equilibrium. That means some changes may occur. Now, to make a change, an infinitely slow process which we call quasi-static, some people call it quasi also, which means nearly static. In Urdu, takriban static. Okay. And this quasi-static process is also the term is used in other branches also, okay, that we may come across. In quasi-static process, as every state, for example, the pressure difference between the system and the surroundings, okay, that goes slowly and with a very small change in the value of pressure, and which infinitesimally small, okay, we call it. Now, let's have a system. Let it be specified by, for a given mass, P, V, T. These are the variables, these are the measurables which you can measure. Now, suppose we wish to take the gas from Pt to P dash T dash by the quasi-static process. We change the external pressure by a very small amount, very small amount, infinitesimally small amount, very slowly, and allow the system to equalize its pressure with that of the surroundings till it becomes equal to P dash. Similarly, if P is not changed, rather T is changed, from T to T dash, similar process, a similar infinite small process is done. As I told you, a thermodynamic system is not always in equilibrium. So let us take two cases. In the case one, I have some gas with a density sigma, and it is partitioned, and this side it is evacuated system. Now imagine that suddenly we take it away, the partition between the two parts. So what will happen? The gas will, when I take this away, then the gas will expand. This side it is vacuum, and the gas will occupy the whole distance. During this process, the thermodynamic equilibrium is not maintained. It will be, there will be an equilibrium, but after a long time, a long wait, we can say now it is again in a state of equilibrium. This is sigma dash, so the density of the gas may change. There is also another possibility. For example, if we have a very simple thing is uh, petroleum vapor and air. They are mixed. The cylinder is there and there is a spark. When the spark is there, then there is a sudden explosion over there. And naturally, then there is a pressure on the piston. The piston moves because of this process that happens. Then also, in both the cases, the systems go into a non-equilibrium state. So, equilibrium states are not very easily achievable, and unless a lot of time has elapsed. So quasi-static process is a hypothetical construct. In practice, the processes that are sufficiently slow and do not involve accelerated motion of a piston. The motion is very slow, it's not accelerated. A large temperature gradient, etc., can be taken as a reasonable approximation to an ideal quasi-static process. There are many processes. What we find is one is called the isothermal process, where delta T is equal to 0. There is no change in the temperature. Iso means the same, thermal means temperature. Similarly, another process is isobaric. Isobaric means that the pressure is constant. Bar stands for barometer, like that, the pressure. Isochoric, where the volume remains the same, does not change. And the adiabatic process, in which there is no entry of energy from either side. So let us take up, and today I wind up this lecture by taking isothermal process. We'll talk about isobaric, isochoric and adiabatic processes in the next lecture. In the isothermal process, we write the ideal gas equation. The gas equation used to be PV is equal to nRT. So, if it isothermal case, the temperature is constant, so nRT becomes a constant. So we can write that the product of pressure and the volume is a constant. And this is what is called Boyle's law. Okay, in the junior classes we did this study about the Boyle's law. If I plot a PV graph, then it is just like the xy is equal to constant, the y is proportional to 1 upon x, I have told you before. So any P1 V1 is equal to P2 V2 is equal to P3 V3, etc., etc. Okay. Now you must have found, particularly in the case of studies of chemistry, that the graph between P and V in the Boyle's law turns out to be a straight line with a negative slope. This is when we plot log of V versus log of P. That could be log to the base 10, that could be log to the base E. So natural log can be taken. So that kind of graph papers are there. And if we plot the values, we find that it is equal to a straight line with a negative slope. So now let us see that a system P1 V1 goes to P2 V2. Okay. At any intermediate state we can say that the value is P plus delta V. A small change in the value of volume, hardly any change in the value of P. So I can write the work done in the system dW. Now I'm using the connotation of differential calculus. dW is equal to PdV, and therefore we can say that integrating both sides, I'll get the work done W is equal to from V1 to V2 PdV, and using the gas equation I can write from PV is equal to nRT. Okay, so I have this divided by capital V here, integral 1 to V2 dV. Now this is the kind of integration that we encountered earlier also, integral 1 upon x dx, which is equal to log natural. So I can write nRT log natural of V2 upon V1. So why is no constant of integration taken over here? Because it is a definite integral. The limits are given. So from one value to the other value, the constant of integration will vanish, and the result we obtain is nRT to log natural of V2 minus log natural of V1. So that is what is obtained, okay, for the work done for the system going from one stage to the other stage, slowly and gradually by the processes. Maybe a QSP kind of thing exists over here. The process is quite slow. You'll find that in the adiabatic process, the things happen suddenly, and we'll talk more about the isothermal process, more about the isobaric, isoporic and adiabatic process in the next lecture, part B of this lecture. Okay, so stay tuned, we meet. Okay, bye.